thank you for being here. And welcome to the next Advanced Tracer session. So let's begin. So my name is Mahmoud Hatem, and I'm an Oracle geek from Tunisia. I also love doing hacking stuff, and I'm also known as the geek man, thanks to Stefan. The weird man, sorry, Stefan is the geek man. So let's get serious. So here is my blog where you can find more information and detail about the different subjects I'm going to cover here. So the session is basically about getting a better understanding of the Linux tracing landscape. I'm going to also show different examples to demonstrate some of the power and capabilities of the different Linux tools. So the basic idea here is to know what can be done, so in case we needed to have to Google that or check the different documentation. So I'm going to begin with a quick overview of the Linux tracing landscape. I'm going to then show different examples using static tracing, dynamic tracing, monkey patching, and the final part of the session will be about how to get a deeper look at CPU utilization. Okay, let's start. And so Linux tracing landscape keep evolving with every kernel release. There is many enhancements that has been embedded in the Linux kernel in the last years. You may have heard about the eBPF, uprob, keyprob, tracepoint, a lot of other stuff. But at first, all this may seem confusing. You may ask how this all stuff are interrelated and where to start. So basically, to get a better understanding of the Linux tracing landscape, we can divide it in three main parts. So we can have the event source, that's from where our tracing data come from. And then we have the mechanism for extracting this tracing data. And finally, we have the front-end tool. Basically, that's the tool we're going to interact with. So in the event source part, we're going to find things such, for example, static tracepoint, dynamic tracepoint, or hardware events known also as performance monitoring counter. So basically, this different hardware event, this different event type, give us great flexibility and instrumenting the thing we want. And then you have the mechanism for extracting this data. An example of such a mechanism is eBPF. eBPF basically is an kernel virtual machine capable of binding action to event. For example, we can have a custom kernel function running whenever we hit a specific kernel tracepoint. And then you have the front-end tool. An example front-end tool, for example, system dev staff or BCC tool or the perf tool. So this different Linux advanced tracer allow us to monitor different event type and layer on the system stack. Okay, let's start by seeing some examples. We're going to begin with static tracing. So static tracing are based on statically defined tracepoint placed by kernel and application developer in strategic location of the code. Based on that, we can write many custom monitoring tool or observability tool. For example, let's say we want to monitor our storage performance or our disk performance, and you are using for that the IOStat tool. But the thing with the IOStat tool, like many traditional Linux tools, is that usually they only show the average latency, which can be misleading. So to overcome this limitation and based on strategically defined tracepoint in the block device layer, we can have a tool to display the full latency distribution, which can be great in this kind of thing. But for application, for example, interacting with the file system, it can be more interesting to analyze the file system performance or the common file system operation latency. And for that, you can use the different tracepoint defined in the file system layer and to build a tool for monitoring common file system operation. The measured latency will, in this case, for example, common file system operation can be a read or write. And in this case, the measured latency will span the actual block device input/output, the file system CPU cycle, file system logs, and the write queue latency, which is, by the way, a great CPU saturation metric compared to the usually used write queue length metric, as it give us a better measure of the magnitude of the problem in case of CPU saturation. And as usual, using the right tracepoint, we can actually have a measure for that for the whole system, or we can also target specific process. can be interesting, for example, if the process are running with different scheduler class or scheduler priority, so to measure the scheduler latency at the process level. And there is a lot of examples and many other tools that you can see. So this is only an extract, only some examples. So you can use them as they are, or you can also decide to customize them. It can be, for example, useful to bring application context to them. For example, let's say that you want to show the actual SQL statement, what that was running at that point, or the actual client defined, or any information that may seem useful to us. So basically, you can have the custom monitoring tool that you want. Let's now take a look at another type of static trace point known as the application trace point or user statically defined trace point. So this type of trace point is basically supported by many common applications such as PostgreSQL or MySQL database, and it allows us to write custom monitoring tool, do advanced troubleshooting and investigation on those applications. But the bad news is that the Oracle database doesn't support this kind of trace point. So how to get new insight in this database? So for that, we will need to take a look at another type of event known as dynamic event, okay, or dynamic trace point. So dynamic trace point allow us to dynamically, as the name suggests, to dynamically put a trace point in a target application without the need to compile it or to restart it. So basically, this is a very great feature. For example, in case of probe, the target instruction that we're gonna instrument or gonna put the probe on is gonna be replaced with software interrupt. So whenever we execute this instruction, our custom function gonna be called. So basically, there is no overhead until enabling this trace point. Based on that, we can trace or investigate the Oracle kernel, which can be useful. But a basic use case will be, for example, to trace a different wait event for a target process. Okay, or maybe we say we can display the wait event histograms. For example, here we are displaying the database file sequential read wait event histograms with microsecond precision, which is great. But for example, we may say, what this wait event is really measuring, and can we really on it to analyze on all other input-output wait event to analyze our storage system and our storage performance? So to answer this question and to check what those wait events are really measuring, we can actually do that by correlating this different wait event with actual input-output syscall. And we can actually, there is already great investigation in this area using the system tab tool. So we can check, for more information on that, we can just check Luca Cani blog. They have very great article on that and with very great results. Okay, so besides also tracing at the function entry and function return boundary of the Oracle core function or Oracle kernel function, we can also trace at different points beyond function boundary. For example, we can trace any function offset. So this is a very rich feature, I think a very powerful feature. For example, by just targeting specific kernel, specific Oracle function offset, we can display the password of every user trying to connect to our Oracle system, even if the password is encrypted over the network, and even if the password is stored encrypted in the data file. Basically, we can have a clear, we can display the clear password. This is basically how we cannot do that. You just have to check which function and which instruction on this function and which register, processor register store this actual password or memory address at this. You just have to check at the exact time. So the investigation, you have to find the exact function. You have to use the NTLP tool that I've covered the last session. I think that's Fritz was here. I'm gonna talk about it